5 years, so.
Well, this is good for you.
Yes. I'm hoping it's all still in there.
It builds character. That's what your parents always used to say. It'll build character.
It does, and it gives me a whole new vocabulary to use in obscure situations.
You'll have a lot more character now.
Yeah.
Okay, folks, let's get started. Happy Wednesday. Usually I've scared off more people by now, so wow. Either that or people have dropped and they're still coming. That's kind of a good thing, too. So, joke. All right. So, hopefully everybody's had a chance to check out the website. I got the videos posted actually late last night. There was a problem with OSU's rendering. So one of the reasons that things go up a little bit later sometimes is if OSU has a problem with their stuff, and my microphone is making too much feedback. So anyway, if that happens, which is what happened this time, it takes a little bit longer. So hopefully that wasn't a problem for anybody. Last time I got talking briefly about hydrogen bonds and the importance of hydrogen bonds. And I'm pretty much going to finish, or just leave that be. I think you get the idea that hydrogen bonds are important. It's important because they are both weak and added together they are strong. And so it makes it easy to break them when we need to break them. And it gives us strength for holding things together when they add up, essentially. All right. Well, you see the next topic on there, which I'm sure many of you love, thermodynamics. I'm not going to say much about thermodynamics, actually. In fact, I think in the interest of moving forwards, we're not going to say anything about thermodynamics right there. Thermodynamics, no, I said I wasn't going to say anything. I'd say something about it, right? So the thermodynamics we will talk about later in the term. And thermodynamics are very important with respect to understanding. That's going to get annoying, isn't it? Very important for understanding directions of reactions and predicting directions of reactions. And we'll see how that comes into play later in the term. Okay? I've got this down a little bit, so if you can't hear me back in the back or something, just wave at me. I can't hear real well what the microphone is doing unless it makes an obnoxious noise like that. Okay. Instead, what I want to focus on now is, again, some more things that I think you probably didn't get covered properly in freshman chemistry. So I want to go through this and make sure everybody's on the same page. All right? So it's important in this class that we understand a tremendous amount about what pH is and how pH affects things. pH is critical because pH is a measure of the concentration of the hydrogen ion concentration of a solution. Okay? pH is the measure of the concentration of the hydrogen ion concentration, I guess, of a solution. All right? Now, that turns out to be very important because protons, of course, are charged. And as we change the concentration of protons, there are many biological groups that can either accept or donate protons. If they accept protons, they gain a plus charge. If they lose a proton, they lose a plus charge. Okay? And so what we see as a result of changes in pH is that biological molecules in solution can change charge. That's very important. Okay? That is very important because one of the important considerations of biological molecules is the fact that when the charge changes, okay, their shape may change. One of the forces holding together proteins are ionic bonds. If we change the charge, if we change something from a 0 to a +1 charge, imagine that I had two groups that were sitting in a protein. One over here is a minus, one over here is a plus. I change the pH so that the minus becomes a 0. What happens to that attractive force that was between them? It's no longer there, right? We can see now that what was a force that was helping to hold this together, plus attracting minus, is now plus to 0, and there's no attractive force holding them together. That protein is going to be destabilized. Its structure is not going to be as strong as it was before. Worse, what if I have a situation where I start out where I have something that has a minus charge, and I have something over here that has a 0 charge, and the thing that has the 0 charge loses its proton? What's going to happen? Not that, I hope. Okay? What's going to happen is the charge is going to change from 0 to -1. Now I've got a -1 to -1. They are going to repel each other, which is going to drive them apart. So now instead of just destabilizing the structure, I'm actually going to change the structure because those repulsive charges are going to push those groups apart further than they were before. Okay? Try this again. Okay, so charge is important. So we have to understand pH, and we have to understand the pH as it affects the proton concentration as it affects biological molecules. All right, well, we start simple. pH, something you memorized in freshman chemistry, you're going to memorize it again. pH is the negative log of the hydrogen ion concentration. Probably everybody here memorized that. Happy going, oh God, logarithms. Well, at least I can plug them into my calculator. No? No calculators in this class. Now panic sets in. Okay? Well, how am I going to get the logarithm of 4? Do I have to memorize all the logarithms? Well, since there's an infinite number of logarithms, that would be a little hard to do. Okay? You have to know how to manipulate them. You have to know how to set them up. I am never going to require you to give me a number that you would punch into a calculator. If you get it to the point where it says logarithm of 4, that's your answer. You write it down. So this is not a class in testing, are you able to punch log 4 in your calculator? It's a question of, can you get to the point of getting to log 4? Okay? Now, we'll see more about that as we go along. I'm going to give you some tips. I'm going to give you some really easy ways to manipulate these things. And I do that because it's important for you to understand what math means. Math is like chemistry, okay? People taught you a whole bunch of stuff. You didn't know what math meant. You didn't know what chemistry meant because they just gave you a bunch of stuff. They poured it into your heads, right? And you were stuck with this stuff. Now, okay, I hope to teach you something about what these things mean. All right? So, we're not going to use calculators. Absolutely. No calculators in the class. All right. Now that we've said that, pH is the negative log of the hydrogen ion concentration. All right? As the pH goes down, the hydrogen ion concentration goes up. And conversely, as the hydrogen ion concentration goes up, pH goes down. Right? As the pH goes up, the hydrogen ion concentration goes down, etc. Right? Makes sense. That's something you probably memorized. Probably everybody's shaking their head. I see a lot of shaking heads going on. You memorized that from freshman chemistry. Okay, I've got that part down. All right. Water is made not only up of water molecules, but it's made up when it dissociates of protons and hydroxyls. That's where the pH business comes from. A pH of 7. Why are we talking about a pH of 7? Well, pH of 7 is what the hydrogen ion concentration is if I take pure water and I set it on the table. Okay? The concentration of hydrogen ions, if I have pure water, is 10 to the minus 7 moles per liter. If I take the negative log of 10 to the minus 7th, I get 7. pH is 7. Okay? So pH is the negative log of the hydrogen ion concentration. I'll give you all this on exam. You don't have to memorize that. Okay? You'll have every equation on the exam that you need. You won't have to memorize a single equation. All right. pOH, by extension. If pH is the negative log of the hydrogen ion concentration, the pOH then must be equal to the negative log of the hydroxide ion concentration. What's the pOH of pure water? 7. Because when I dissociate water, I get 1 proton, I get 1 hydroxide. So if I have 10 to the minus 7th protons, I have 10 to the minus 7th hydroxides. Right? Well, that's kind of cool. So pH plus pOH equals, you can do the math, 14. If I have a solution that has a pH of 6, you can quickly do the math, and I hope you won't need a calculator for that. You can determine that the pOH is 8. Because they always add up to 14. Okay, that's nice. That's simple. Right? You're supposed to say, yes, professor. Okay, that's simple. All right. So, that's nice. Now, when you were in freshman chemistry, you took HCl and you put it into solution. In fact, one of the first things you ever probably did when you were in chemistry in high school was go, oh, wow, man, get to work with acid. Get to eat up some bolts or something like that. I mean, that was, for me, that was the biggest thing when the first time I took high school chemistry. You could watch all those bubbles coming off and everything. That was cool. HCl made that happen. HCl was useful for doing pH problems because HCl has a very, very useful and simple property that you probably didn't pay too much attention to at the time. And the useful property is that HCl completely dissociates in water. If I put in 1,000,000 HCl molecules into a beaker, I end up with 1,000,000 protons and 1,000,000 chloride ions, and I have 0 HCl's left. 0. Completely dissociates means completely comes apart. So if I have 1 liter of solution and I have 0.1 moles of HCl that I put into it, that means I will have 0.1 moles of protons, 0.1 moles of chloride. The chloride doesn't affect the pH. The concentration of protons is 0.1 molar. The negative log of 0.1 is equal to 1. Okay? I've got a pH of 1. Now, for strong acids, if I know the amount of material I start with, I know how many protons I've got. Right? Very simple. Yeah, I did this in freshman chemistry, and that was probably something in freshman chemistry you got and you sort of retained. Unfortunately, they probably didn't tell you, or maybe they told you but it didn't sink in on you, that not all acids are strong acids. They're not. Not all acids are strong acids. But you're going to want all acids to be strong acids in your head, because that's the way you've always worked pH problems. Oh, take this amount, I know how many protons I got, da-da-da. Doesn't work that way. Doesn't work that way. So, what is an acid that's not a strong acid? I'll give you a definition. An acid that is not a strong acid is something that does not completely dissociate in water. If I put it in water, only some of it comes apart. Only some of it comes apart. So, example, my favorite acid I talk about is acetic acid. Here it is, HAC. The H referring to the proton attached to it. The AC referring to the acetate, which is what we call the salt part of it. Okay? When I put acetic acid into water, first of all, I make vinegar. Okay? I put acetic acid into water, that acetic acid comes apart. HAC becomes H plus and AC minus, except for if I started with 1,000,000 HACs, I will not get 1,000,000 protons and 1,000,000 AC minuses. Won't get it. Okay? I won't get that. Now, well, the question is, well, how many of those did I get? What is the pH of that solution? That's really what I want to know. Okay? So I have to have some other things to help me to calculate the pH of that solution. I don't know what that is. Now, that's one of the things we're going to work on doing. We're going to understand how to calculate the pH of a solution that has a weak acid in it. Okay? Everybody glum now? Getting to the hard part of the course, second day. By the way, most of the calculations we do in the course is in the first part of the course. If you don't like calculations, then bear with us. They will hopefully get better. But you will have to do some calculations. All right. Well, acetic acid, to give you an idea, is a pretty weak acid. Okay? If I take, let's say, 10,000 acetic acids and I put them in solution, 10,000 molecules of acetic acid and I put it into solution, I basically get 1 H plus and 1 AC minus. Every time I make an H plus, I make an AC minus. How many does that leave me for HAC? 9,999. That's very different than I had with HCl. I didn't have that many with HCl. I've got 9,999 that are still sitting there. Okay? Those guys that are sitting there have protons, and if I do something to that solution, those protons can still come off. And in fact, we're going to see how we can pull them off in just a little bit. But if I don't do anything else, they will just sit there in solution as they are. Okay? You with me? All right. So that gives you an idea what a weak acid is compared to a strong acid. Okay? How many people remember the acid dissociation constant from freshman chemistry? They must not have covered it when you were there, or perhaps you were all asleep. They didn't talk about the acid dissociation constant? Okay? All right. Ka. All right. So if we look at the dissociation of water, water goes to H plus and OH minus. All right. Water is, in that case, a simple acid. we can apply the same thing to a weak acid. The dissociation constant here, Ka, gives us the equation that the dissociation constant is equal to the concentration of the AC minus. And by the way, we're going to have a name for the AC minus. You're going to want to call it base. And we're not going to use the term base in this class except in one circumstance. The only time we're going to refer to the word base is when we have a strong base. AC minus is not a strong base. It's a salt. Okay? So the thing that is left from a weak acid when you pull the proton off is a salt. AC minus is a salt. Okay? The dissociation constant for an acid is equal to the concentration of the salt times the concentration of the proton divided by the concentration of the overall molecule. And you're not going to like this because the overall molecule is the acid. You memorized in freshman chemistry that the proton is the acid. It's not. The thing that gives up the proton is the acid. HAC is an acid. It's a weak acid, but it's an acid. So, get those terms down. Salt is what happens when you take a weak acid, you pull the proton off. The acid is the thing that had the proton. So an acid, a weak acid, will always, you want a good rule, always have one more proton than a salt. HAC has one more proton than AC minus. Okay? All right, so there's an equation, blah, blah. What does that equation mean? Well, that equation tells us it's actually a measure of how much dissociation happens for this particular acid. We could write this for anyone. We could write this for formic acid if we wanted to. Same equation, we'd have formate there instead of acetate, and we'd have H-formate over there instead of acetate, but the same thing. Okay? The more protons that are produced, the stronger the acid. Okay? The more protons that are produced, the stronger the acid. The larger the Ka value, okay? The larger the Ka value, the stronger the acid, because a large Ka value corresponds to more protons. Right? All right, so I've got more protons. I have large Ka value. That means strong acid. Well, I told you that pH was equal to the negative log of the hydrogen ion concentration. I told you that pOH was the negative log of the hydroxide ion concentration. Now I will ask you, what's the pKa? It's the negative log of the Ka. If I said, what is the P Kevin Ahern, you would tell me it is the negative log of Kevin Ahern. Right? Just by extension. All right. So now we've got a new term. We've got a term called pKa, and pKa is a measure of the strength of an acid. We won't talk about Ka after this probably at all. Okay? The pKa is a measure of the strength of the acid. As the Ka went up, the acid got stronger. As the pKa goes down, the acid is stronger.
How is that different than pH?
How is that different from pH? Because pH is simply a measure of the proton concentration. This is a measure of this entire equation. Okay? She asked, well, how is pKa different from pH? And by the way, I always forget to do this, but when you ask questions, I will try to repeat the question because people on video always go, what'd they say? Okay? And my brain dead mind doesn't always remember to repeat the question, but that's what I will try to do. Now, as the pKa goes down, the strength of the acid goes up. Right? So if I have two weak acids, okay, I gave you the example of formic acid. Formic acid has a pKa of 3.75. We'll talk about those numbers in a minute. Acetic acid has a pKa of 4.76. That tells us, first of all, that formic acid is a stronger acid than acetic acid is because it has a lower pKa. A stronger acid, by definition, will be more dissociated. It will have given up more protons when you put it in water than acetic acid would when you put it in water. So we have degrees of strength among the weak acids. Degrees of strength. If a molecule has a pKa, it is a weak acid. HCl completely dissociates. It does not have a pKa. Okay? Molecule dissociates completely. It doesn't have a pKa. If it has a pKa, it is a weak acid. Now, that's a very important thing for us because we're going to see that things that have pKa's have very, very important biological significance. Very important biological significance. Okay? Questions about pKa? I can't see with that light. No question? Am I that clear or am I that cloudy? No comment at all. Okay. Well, hopefully. Let's see what we have here. So, why does this thing keep going out? There we go. pKa. So, the lower the pKa for an acid is, the stronger the acid, the larger the pKa, the weaker the acid is. Okay? That'll be important for us. pKa is a constant for a given acid. Underline that in your notes as well. pKa is a constant for a given acid. Whenever I'm talking about acetic acid, or as we commonly refer to it, an acetate buffer, which we'll talk about in a second, it will always, always, always have a pKa of 4.76. That will never, ever in a million years change. You go on Mars and you do the experiment, it'll have a pKa of 4.76. Formic acid will always have a pKa of 3.75. And no, you don't have to memorize any pKa's either. After you taught this class a few years, you learned to anticipate the questions. Okay? So, you understand what pKa is a constant for a given acid then, right? All right. So, now we move to something else. Okay? So I already told you once that strong acids completely dissociate, meaning I put a million HCl's in there, I get a million protons, I get a million chlorides. I said we will not use the term base in this class except for under one circumstance, and that is where we have a strong base. Weak bases are very confusing. We're not going to talk about them. Okay? I'm not going to talk about them. We're not going to talk about conjugate acids and conjugate bases and all that. We're going to talk about acids and salts. Very simple. Simple is good. Okay. Now, a strong base, however, by extension, is a molecule that when we put it into solution, completely dissociates into hydroxide and something else. A strong base is something that when we put it into solution, completely dissociates into hydroxide and something else. In this case, it's sodium hydroxide, it could be potassium hydroxide, it could be strontium hydroxide. It doesn't really matter. Okay? So, NaOH, sodium hydroxide, is a strong base. That means if I start with a million NaOHs and I put a million NaOHs in water, I will get a million OH minuses and a million Na pluses. The Na pluses won't affect the solution. Yes, ma'am?
So when we're dissociating acids, we get a proton and a salt. If we're dissociating bases, we get the OH and what?
Okay, so our question was if you dissociate you're talking about an HAC, a weak acid?
No, like when you dissociate the strong base.
Okay,
Instead,
so when you...
strong base, we're called salts.
Okay.
So what do we call it?
Well, you can. I would just call this chloride and sodium. I wouldn't give it a name, because if you call it salt, you're going to confuse it with this salt. Okay? So salt is something, in our class, we're defining as something that's produced by the dissociation of a weak acid. Everything else is either sodium or, in this case, chloride. Okay? Good question. All right. Well, so we've got strong bases. Why do we care about strong bases with this? Okay? We're not going to talk about bases. Why do we talk about strong bases? Well, it's a very important thing. Okay? If I take, let's imagine for a moment I take some HAC, that is acetic acid. I take acetic acid and I put it into water. I said maybe 1 in 10,000 of these guys with a proton coming off. Most of them are sitting there with the proton on. Okay? Here's what happens in the reaction. Okay? HAC goes to H plus AC minus. Notice that little arrow meaning both directions. Equilibrium. The other thing that you never got out of freshman chemistry was that equilibrium doesn't mean equal. Equilibrium does not mean equal. Equilibrium means no change in concentration over time. Once I put it in there, the concentration stays the same. It means that the forward reaction, which is the reaction that's making these two products, is the same as the reverse reaction. Therefore, no change in concentration over time. This is an equilibrium. Everything in this course is going to be at equilibrium unless we disturb it. And when we disturb it, it will instantly change. instantly. So in essence, everything is always going to be at equilibrium, except for that instant when we change it. Now, why do I tell you this? Well, here's what I did. I took that HAC, I put it into water, I got H plus, I got AC minus. Okay? And if I didn't do anything else, it's just going to sit there like that forever. However, if I started adding some sodium hydroxide to this solution, something is going to happen. Okay? When you were in freshman chemistry, you took HCl and you added NaOH, and you probably measured the pH as a function of how many drops you added. Do you remember doing this titration experiment? Right? And the pH all of a sudden went boing, right? Why did the pH change when I had HCl and I started adding NaOH? Why does the pH change? What's that? You make water, and making water does what? Removes hydrogen ions. So when I add hydroxides, I lose hydrogen ions. Okay? How many people know what Le Chatelier's principle is? Everybody should know this. There's something you should have gotten out of freshman chemistry. It's not your fault. Why didn't they pound this in your head? Le Chatelier's principle says this. When you disturb the equilibrium of a system, the system will strive to reestablish it. Okay? When you disturb the equilibrium, the system strives to reestablish it. When I add hydroxides to a solution, they start gobbling up protons. The proton concentration goes down. Right? This, what we're getting ready to talk about, is a prime example of Le Chatelier's principle. If I start adding OHs to this, what's going to happen to the concentration of protons in this solution? It's going to start to go down. Is that the end of the story? It's not the end of the story. And the reason it's not is we have another source of protons over here. We have another source of protons over there. Okay? It's like a reserve, if you want to think about it that way. Remember those 10,000 I had, and I had 9,999 sitting over here? Well, I start taking these guys away. What happens is when I start adding OH, I'm going to start breaking down HAC. HAC is going to start giving up protons to try to replace the protons that were lost. Okay? I've just disturbed the equilibrium. The system is now trying to reestablish itself. Well, let's imagine, if you will, that I had 9,999 HACs. I had one H plus and I had one AC minus. If I add one at a time protons to, OHs to this, NaOH, what's going to happen? Every time I add one proton, I'm going to see one HAC break down, replace that proton, and make an AC minus. Let's imagine I do that 500 times. What's going to happen? Better yet, let's do it 499 times. Well, if I start out with 9,999 HACs, I'm going to end up with this at the end with 4,500 AC minuses. How many protons am I going to have left? That I don't actually know. Okay? That I don't actually know. That's where we're going to have to invoke, okay, something besides that microphone. That's where we're going to have to invoke an equation to help us calculate what the hydrogen ion concentration is. The principle I've just given you is a very important one. If there's one thing you want to take away from what I've just told you today, it's that right there. When I take this system and I start adding hydroxides to it, I start losing acid and making salt. For every OH that I add, I lose one acid and I make one salt. Okay? Make sure you get that in your head. Well, let's say, okay, I keep adding and I keep adding, so I had 5,000 of everything to start with, and I add enough so that I end up with 2,500 AC minuses and 2,500 HACs. Okay? I have equal amounts of salt and acid. Everybody envision that? I've added enough NaOH to do that. Okay? When I add that, okay, I get to this point, I've got equal amounts of salt and acid. Well, somebody says, oh, wait, we didn't want to add all that stuff. Let's add back some HCl. I've got 2,500, I got 2,500, I start adding HCl. What's going to happen?
More protons.
I'm adding more protons, right? I'm going to disturb the equilibrium again. And the system's going to try to reestablish itself. How is it going to do it? It's going to start gobbling those protons up because I've dumped protons in. We'll show you. We're going to take them away. AC minus is going to grab those protons, and the reaction that was going to the right is now going to go back to the left. That makes sense? Now, seeing how this equation goes back and forth and how it's manipulated is very, very important. Okay? Because this equation lets us make AC minus, make HAC, or break them down as we choose. Now, we'll see why that's important later. But in order to do this, I must have a strong acid or a strong base. If I add a weak acid or a weak base, which we're not going to talk about, it gets much more complicated. We're not going to do that. We're always going to have a situation of a weak acid with which we're going to either add a weak base, a strong base, or a strong acid. Okay? All right. Does everybody understand how this equation is going back and forth? If you don't, please raise your hand. Everybody's got it? Okay, pop quiz. Pull out a piece of paper. You just said you had it. I'm joking. Okay. But you know, you should always be honest, right? If you didn't get something, you should raise your hand and ask questions because you never know, we might have a pop quiz. In which case, I'll see how truthful you were about how much you knew. And your name will be there, and there'll be like a great big zero. You'll go, Kevin knows I wasn't telling the truth, right? Yes?
When you're adding a strong base,
Yes.
how many more bases are there?
When I'm adding a strong base, the pH is going to go up. That's correct.
So when it's bases, and then you add strong acid,
Yep.
and you're making more acetic acid,
Yep.
will you change the pH as fast because you don't have any H bonds?
Okay, so our question was if I have this system and I add a strong base, what happens to the pH? The pH will go up, absolutely. And then if I have that solution that has already had its elevated pH and I add HCl, what's going to happen? The pH is going to go down. Okay? It's as simple as that. Now, what we're going to see is that the system is going to change its pH very little within certain ranges. It's not going to go up very much if we're careful, and it's not going to go down very much if we're careful. That is fundamentally important for biological systems. Because big pH changes cause big charge changes, and I've already hopefully told you that big charge changes cause proteins to fall apart. We have to have something that resists those changes in pH. We can't stop pH change completely, but we can resist them. And that's what we're getting ready to talk about. Resisting changes in pH. Okay, other questions? Okay, well, that brings us to the topic of buffers. Okay, buffers. Here's the definition for you. A buffer is a system that resists change in pH. It's a system that resists change in pH. What is a system? A system has a weak acid and a salt. A system has a weak acid and a salt. A buffer is a system that resists change in pH. Therefore, a buffer is a combination of a weak acid and a salt that resists change in pH. It resists change. Yes, ma'am? Sure. So a buffer is a system that resists change in pH. Okay. The system has a salt, it has a weak acid. So a buffer is therefore something that has a weak acid and a salt, and it resists change in pH. Okay. So, what does this mean? What does this mean? Well, in freshman chemistry, you did titrations. And titrations, when you did it with HCl and NaOH, you saw that as you added OH, you saw that pH just go crazy. If you did it with a buffer, you probably didn't see that pH change so drastically. In fact, you might have seen something that looks like this. Now, this is the first graph that you're seeing this term. I'm a firm believer in you should know what a graph tells you. Again, I believe in practical use of mathematics, practical use of chemistry, not memorize things. For many of you, that graph is, oh, I can memorize that shape. That's what it looks like, right? What does this mean? This is a plot of pH versus equivalence of OH added. Okay? For the moment, we'll just think of equivalence as relative amounts of OH. All right? pH on the y-axis, equivalent amounts of OH on the x-axis. Whenever you learn a graph, the first thing you should always do is you should always, what are the axes? Okay? Without axis information, a graph doesn't have any meaning. If I ask you to graph something on an exam and you don't put any axis on there, that is, you don't label the axes, you can have a beautiful shape. You're going to get 0 on the graph because the shape has no meaning without axes. You have to label the axes. That is critical. This is telling me that as the pH, as I add more and more OH, the pH of this solution is going to go up. Right? That's the first thing it tells me, because look, I keep going more and more OH to the right. pH starts out here and it goes up, 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 up. Okay? This also tells me something different. That there's a region in this plot where the pH doesn't go up so fast. That is, if I go from here to here, the pH goes from about 1 to 2. If I go that equivalent distance from here to here, the pH goes from there to about 2.4. It doesn't go up nearly as fast. The same amount of hydroxides going from here to here change the pH much more than the hydroxides, same amount of hydroxides going from there to there. What you're seeing graphically is the effect of the buffer. The buffer is resisting changes in pH. It's resisting that. Okay? You know what I'm going to do? That thing is driving me nuts. I'm just going to yell. If you can't hear me, let me know and I'll turn it back on. But that thing is really annoying. Okay, so the buffer is resisting change in pH. All right? How is it resisting it? How does a buffer stop the proton concentration from changing so drastically? How does it do that? Okay? Well, you already know the answer to that. You already know the answer to that. Remember how we had that HAC and we had that AC minus? I said when I started adding protons to that mixture, if I added protons and I had, say, equal amounts of the two, one would start gobbling the protons up. Those protons would not directly change the pH, which is what would happen if there were nothing there. Something starts gobbling the protons up, the proton concentration can't change very much. The AC minus is grabbing those excess protons that I add. What if I added the sodium hydroxide? Well, the HAC started giving up protons to replace that which was lost. Now we see why a weak acid and a salt combination are very, very important for understanding how pH is resisted. Okay? Notice how this plot goes up, it flattens, and it goes up again. What do you suppose is happening at the place where it flattens? What does flattening mean, graphically? So we see we're adding more and more OH, and we don't really see much change. This could be the place at which we say we have the maximum ability to resist change in pH. This is what I will call the maximum buffering capacity. Right there where that dot is, that's the flattest part of that graph, that's where I have maximum buffering capacity. Well, do you suppose this is the place where I had 9,999 HACs and 1 AC minus? Do you suppose it's the point where I had 9,999 AC minuses and 1 HAC? Two extremes, right? No. This point is the place where I had 2,500 HACs and 2,500 AC minuses. Maximum buffering capacity occurs when salt equals acid. We have the maximum ability to flip one way or the other, either giving up protons or absorbing protons. That is maximum buffering capacity. Okay? The pKa, yes?
Why is it not logarithmic rather than exponential? Because every time you go from 1 pH, it's times 10, so
It is logarithmic. That's a log scale right there.
I meant the shape of the graph rather than the axes.
I'm not sure I understand your question, but since we're already plotting a logarithmic plot, it is a those are logarithms. That's the negative log of the hydrogen ion concentration. If we were plotting the hydrogen ion concentration, it would look different. Okay? Okay, so this point, that point right there, is the place where I have maximum buffering capacity. Okay? Maximum buffering capacity. Maximum buffering capacity, what I say is it turns out, is what the pKa actually is. So that pKa that I said was the negative log of the Ka turns out to be very useful. That is the place at which the amount of salt and the amount of acid in solution are the same. For this particular acid, the pKa is about 2.5. How did I get that? Well, I went to the flat place, I read the pH off at the side, and there it was. So not only is pKa the negative log of the Ka, the pKa is the pH at which the buffer has maximum buffering capacity.
It's also the dissociation constant.
It's the negative log of the dissociation constant. It's not the dissociation constant. Okay, so if I gave you a graph like this, you could read off the pKa and do that. If I gave you the pKa of a solution, I said the pKa of this acid was 6.4, you could probably get a pretty good idea what that graph's going to look like, right? It's going to go up, get up to about 6.4, it's going to level off, but it's going to go up again. Why does it go back up again? Why do we have these different regions? Why does it go up? Why doesn't it just flatten out? We got a buffer, right? What's that? I used it up. I've got a fixed amount of buffer. I had 5,000 molecules. When I use those up, what happens? I don't have a buffer anymore. When I use up my buffer, I don't have any buffer anymore. Now I'm at the whim of however many hydroxides I add. Make sense? Whenever I exceed my buffering capacity, I'm in trouble. Let's imagine I have a solution that I started with acetic acid that was 0.1 molar acetic acid. How much NaOH would I have to add to get to maximum buffering capacity? Do the math, guys. How do we get to maximum buffering capacity? What does it take to have maximum buffering capacity? Equal amounts of salt and acid, right? So how much NaOH would I have to add to have, first of all, how much am I going to have if I have equal amounts? I can't hear you. I start with 0.1 molar HAC, right? If I want to have equal amounts of AC minus and HAC, what am I going to have in terms of concentration? 0.05 molar of each, right? How will I get 0.05 molar of AC minus? I'm going to add 0.05 molar NaOH. Now I know how to get a buffer to maximum buffering capacity. That's very useful. Let's imagine instead that I started with that buffer of 0.1 molar and I added 0.2 moles of NaOH. What am I going to have at that point? Problems, right? This is where practical math makes sense. In the first case, you said, well, I had 0.05, I subtract 0.05 from 0.1, and I get 0.05, and I'm set. If you use math here without thinking about what this means, you get something that doesn't make any sense. I had 0.1 molar, and now I had 0.2 molar NaOH, therefore I'm left with minus 0.1 molar HAC. It means I've entered a black hole, folks. That you can't have minus 0.1 molar. Math has to have a meaning. Okay? All right, so the buffer has a limited capacity. One of the problems that you're going to see in the recitations and on the assignments is that you're going to work a problem that's not going to make any sense. And I'll give you a clue. It's because you're exceeding the buffer's capacity. You're going to exceed the buffer's capacity. Think about that when you're working through those problems. Okay. Questions? We got a little bit more to go. We have an equation to do yet. Oh boy. All right. Well, let us introduce an equation you're going to hear a lot about because it explains mathematically what I just told you graphically and in words. This equation is called the Henderson-Hasselbalch Equation. And it should be spelled up there somewhere for you. There you go, right there. Henderson-Hasselbalch Equation. The Henderson-Hasselbalch Equation shows that there's a relationship between the pH of a solution, the pKa of the weak acid in it, and the concentration of salt and acid. Specifically, it says that pH equals pKa plus the log, the concentration of salt divided by the concentration of the acid. Okay? I'll give you the equation on the exam. You don't need to memorize it, but you need to know how to use it. That's the important thing. Let's think about this. pH equals pKa plus log of salt over acid. When do we have maximum buffering capacity? Salt equals acid, right? So if I have log of AC minus over HAC, and that ratio is 1, what is the log of 1? It's 0. Now you know why pH equals pKa when you have maximum buffering capacity. When you had maximum buffering capacity, you had equal amounts of salt and acid. That log term became 0, therefore pH equals pKa. So the pKa is simply a pH. It's a pH at which salt equals acid. It's the pH at which we have maximum buffering capacity. Okay? Let's say I'm at maximum buffering capacity. I've got those 2,500 ions of each one. And I add some sodium hydroxide to that solution. What's going to happen to that solution? What are those hydroxides going to do? It's going to gobble up protons, right? When I gobble up protons, what's going to happen to the concentration of HAC? It's going to go down, right? Because HAC is going to give up protons to replace it. HAC concentration goes down. What happens to the concentration of AC minus? It's going to go up. That log term is now going to be greater than 1, right? Before it was equal. AC minus is going up. HAC is going down. The log term now is greater than 1. What is the log of a number greater than 1? Well, it depends on what the number is, right? Yeah. But what's the value of it? Is it plus or is it minus? It's plus. The log of a number greater than 1, and I'll put this in the exam too. The log of a number greater than 1 is positive. Did the pH go up from where it was before, or did it go down? Use the equation. What does the equation tell you? It went up. Because I had a number that was pH equals pKa, and I added a positive number to it. That means that that sum must have gone up. Therefore, the pH was higher. The pH will be above the pKa when the salt is greater than the acid. Conversely, the pH will be less than the pKa when the salt is less than the acid. How would I get salt less than the acid? What would I have to add? Strong acid, HCl, right? Now, I'm not going to go through and work problems in here because I don't have a blackboard and a good way to do it. So one of the things that your TAs are going to do is they're going to go through these things with you and work problems for you. Okay? They're going to work through these problems for you. The number one thing I want you to be thinking about as you're working problems is think practically. Don't memorize ways to do things. You'll get in trouble. You'll go into a black hole. If anybody disappears from this class, I know what happened to them. They tried to work a problem and they created a negative amount of a solution and they were in a black hole. Okay, so you guys are acting like the class is done. Okay, the class is done. All right. Hi, Kayla. This is Kevin in my own hall. I've been having a lot of trouble with this microphone. As I walk around the room, it just keeps ringing and ringing. So, nope.